Alright, Assalamualaikum and good day to all. So we start with learning unit 1. I have explained the course assessment in our synchronous briefing that day previously. Okay, so we will have at least 2 quizzes, okay, 5%, 2 assignments, okay, 25% midterm exam, 30%, and final exam 40%, and all of these are mapped to the CLO of the course, which I already have explained also. So the first learning unit is Analytical Chemistry Overview. I have started it in the class, so I'm going to repeat it again. So these are the learning objectives that you should be able to accomplish by the end of this learning unit. Okay, defining analytical chemistry, okay, and explain its application. Secondly, distinguish and explain quantitative analysis and qualitative analysis. So you should be able to differentiate between quantitative and also qualitative. Next is explain the steps involved in chemical analysis, specifically quantitative analysis. Next is understanding common analytical problems. So what are the common problems that normally occur with regard to analytical chemistry? Next is explaining quality assurance in analytical chemistry. And then last is slight introduction to different units of concentration, and we will focus more on this in the second learning unit. So the definition of analytical chemistry by Valcasel in 1997 is a metrological science that develop, optimize, and apply measuring processes intended to derive quality chemical information of both global and partial type in order to solve the measuring problems posed. So what it means here, okay, basically is a metrological science. Okay, so metrological science is science of measurement. Okay, and then based on the definition, okay, what it means is that it possesses a dual character. So it develop and it apply, okay, in practical situation. So for example, before we measure, nowadays we can measure pH of any solution, okay, because the method has been developed on how to measure pH of a solution. Okay, so measuring pH is the practical part or the application part, and then the method used to measure the pH has been developed in the past by the previous chemists. Okay, the next one is analytical chemistry. We deliver information, okay, based on that dual characteristic, develop and apply. It gives you information. For example, just now, it gives you information of the pH of the solution. Okay. And then lastly, it regards measuring processes that can be called analytical processes, okay, as the vehicles for obtaining information. Okay, so what are the processes involved in the measuring of the pH? So you have to calibrate first the pH meter. Okay, so those are the processes involved, okay, in order for us to obtain the information, which is the pH of the solution. So these are the application of analytical chemistry in almost all branch of our life, okay, almost all category. Okay, analytical chemistry are used in environmental sciences, in geology, in biology, in chemistry, in physics, in engineering, medicine, material science, and many more. Okay. For example, you are a zoology student, so you want to measure animals' characteristic. Okay, what is the length of the feather of a bird, for example? Okay, so it involves measurement. Okay, so you measure Okay, how long is the bird's feather? Okay, so those are example of antical chemistry in many branches uh, 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 of our life. Okay, like engineering. Okay, you make building, so it composed of bricks. So bricks are made of what? Okay, and what are the component of the bricks? Uh, how much of um, um, soil? How much water? Okay, and then it undergo baking. Okay, at high temperature. What is the temperature? How long? Okay, those are all ethical chemistry. You eat medicine when you feel dizzy. Okay, Panadol. So Panadol is made of chemical. Okay, paracetamol. Okay, so those are ethical chemistry that you are sometimes you are not aware of. Okay, so these are the three terms that you will normally encounter under ethical chemistry. So you very frequently see these terms, okay, throughout this course. The first term is analysis. So what does analysis means? Okay, provide chemical or physical information about a sample. So when you do analysis, you want to find information of a sample. Okay, it can be both physical and chemical. It can be only chemical or it can be physical. Depends on your need. Okay, or the customer need when you do analysis. The second term is analyte. So the analyte is the component of the sample that are to be determined. Okay, means the component of interest. So you want to measure pH of water. So your sample is water. Okay, your sample, the analyte is the water. Okay, the third term is determination. Okay, determination is analysis of the sample. Okay, to find information of the sample, such as the identity, the concentration of the component in the sample, or the properties of the analyte. Okay. So next we move on to qualitative and quantitative analysis. So what does it mean by qualitative analysis? So you look at the word qualitative. So it actually comes from the word quality. Okay, so it's actually answering the question what. Okay, for example, what are found in your drinking water? So what are the chemicals found in drinking water? So examples are iron and also zinc. Okay, when it comes to quantitative analysis, means it comes from the word quantity. It's actually answering the question of how much. Okay, how much. So means you must have a value. Okay, for example, what are found in your drinking water? Okay, and how much? So we write, for example here, 0.05 ppm of iron, 0.01 ppm of zinc. So you have value here. Okay, value. Okay, number. So that is quantitative analysis. Okay, very easy differentiation between qualitative analysis and quantitative analysis. Next, we move on to different types of quantitative analysis. So the first one is gravimetric analysis. So gravimetric analysis comes from the word gravity. Gravity means it has to do with weight. Okay, measured weight. For example, how much suspended solid in water sample. Okay, so to find this, okay, we have a water sample. We filter the water sample because suspended means the one cannot dissolve in the water. So once we filter, we separate the one that the water itself and the sample that does not dissolve. So that is suspended solid. The second type of quantitative analysis is volumetric analysis. So it comes from the word volume. Okay, so it means a measured volume. Okay, volume means the unit has to be in milliliter or liter. Okay, so for example, to determine acidity of a sample of vegetable oil, Okay, by measuring the amount of base needed to neutralize the sample water. So means it involved titration method here. So we titrate the vegetable oil with base so that we know the acidity of the vegetable oil. Okay, normally volumetric analysis will involve the formula M1V1, M2V2. Okay, so when we know the amount, okay, the amount and the concentration of the titrant, and also of course the predetermined volume of the sample, we know the concentration, means the acidity, okay, of the sample. The next quantitative analysis is electroanalytical method. So electroanalytical methods mean it needs the usage of simple instrumentation that would use um, electricity. For example, we measure potential, we measure current. Okay, so we use multimeter, for example. So multimeter will measure all, we measure potential, it measure the current, and so on. Okay, so example is electrochemical cell. Okay, where we have two electrode submerged in two copper sulfate solution, which are different in terms of concentration, and they are connected through a salt bridge. So I'm sure you have done this in your secondary school. Okay, so we measure the potential or the current that flows through the sample. So the next quantitative analysis is chromatography. So we will look into much more detail of chromatographic techniques in the last learning unit. So what does chromatography mean? It's actually a separation method. Okay, we separate a mixture into its individual component, and this can be done based on interaction with two different phase. Okay, so we have two different phase. Okay, the stationary phase and also the mobile phase. Okay, so we'll look into more detail in the last learning unit. So the last quantitative analysis is spectroscopy. So spectroscopy normally will use the high-end instrumentation. Okay, and this technique will involve interaction of the analyte with electromagnetic radiation, for example nuclear magnetic resonance spectroscopy, NMR, Fourier transform infrared, FTIR, okay, or UV, okay, UV visible spectrometer. Okay, so these are the different quantitative analysis method, okay, and their precision, their sensitivity, their selectivity, and even their speed capability. Okay, so you can just go through this. Okay, for example, when we do gravimetric analysis, okay, uh, it it can only detect this range of concentration of sample, okay, which is not really selective, so that's why it's poor to moderate, and the speed is rather slow because we need to mix two different solution in order for it to form precipitate, and then you have to let it, and then we have to filter the precipitate out of the solution, the remaining solution, and then you have to dry in the oven until it totally dry. Okay, so it's gonna be rather slow in terms of speed. Cost, of course, lower because it doesn't need the use of high-end instrument. Normally, if we use high-end instrument like spectrophotometry, fluorometry, atomic spectroscopy, normally the cost is quite high. Okay, because of the high instrument. So you can see here. Okay, moderate to high. Okay. Of course, when we use high-end instrument, the speed is rather fast, okay, moderate to fast, okay. And if you look at range of detection, also can detect a rather small concentration of sample, and of course precision is rather good, okay. The range of precision is rather good, okay. Okay, next we move on to the steps involved in quantitative analysis. So there are 9 steps involved, okay. The first one is defining a problem, okay. So what are the factors that normally involved when we define a problem, okay. So when we define a problem means what needs to be found, what needs to be analyzed, what is your intention of information that you want to achieve or get, okay. And once you get the information, what will the information be used for, okay. Who will use it, when will it be needed? So these are the questions that normally involve when we define a problem, okay. How accurate and precise does it have to be? So if you want the result to be very accurate and very precise, you have to select appropriate method which can give you good accuracy and precision, okay. What is the budget? If you want good accuracy and precision, means the budget has to be high also, okay. And then the analyst should consult the client so that use so that you can plan a useful and efficient analysis, okay, in term of how to obtain a useful sample, so you don't waste money, okay. So it goes back to the client how much the budget that they are that are allocated for that particular analysis. So the second method, once we have identified the problem, then we select appropriate method, okay. To select method, these are the factors that has to be considered, okay. The sample type, the size of the sample, sample preparation needed, the concentration and range, the selectivity, the accuracy or precision, the instrument, the expertise, the cost, the speed, okay. And then if in high-end instrument are used, does the instrument is is automated or not, or we have to put the sample one by one, okay. And are the methods available in the chemical literature, okay. Are the standard methods available, okay. So when you select method, normally it goes back to standard method. It must have a standard method. So for example, you want to determine river water sample, and you want to identify, okay, goes back to the problem, is the river water polluted, okay. So if it's polluted, what are the methods that is suitable to analyze the river water, okay, to conclude whether it's polluted or not. So these are the factors that need to include. And then the third method, we go for sampling, okay. What does sampling means? Okay, it's obtaining a small mass of a material whereby the composition represent the bulk sample. For example, you want to measure the river water sample because your hypothesis is that the river water is polluted. Are you going to collect the whole water? No, until you drain out the river water? No. Okay, you only will obtain a small mass, okay, which would able to represent the river itself. Okay, so selecting the sampling point is important. Um, would you do the sampling uh, on the surface of the water, at the deeper depth, okay, near the ocean, or in between. Okay, so that is important. Okay, that's why it is the most difficult step to do sampling. Okay, sometimes wrong um, um, decision of the sampling area would gives you um, the data that is not representing the whole the bulk of the sample. Okay, the next step is preparation of lab sample. Okay, so once you have collected the sample, how you going to treat the sample? Okay, so you have to convert the sample to a usable form for chemical analysis. If the sample is in solid form, it has to go on drying, it has to go sample weighing, it has to go it has to undergo mixing. Okay, for example, solid sample have to be ground, okay, to obtain suitable particle size which are homogeneous, so that you get a homogeneous sample. Tak ada sampel yang besar, tak ada sampel yang kecil, sama besar. Okay, so the analysis will be fair. And then mix. Okay, mix. Once you have prepared the sample, how you gonna store the sample? Okay, if the sample is sensitive, you might have to put some acid inside, or you put it in the fridge, for example. Or if not sensitive enough, you can just leave it in the room temperature. Okay, so it depends on the type of sample to be analyzed. So it all goes back it all goes back to the standard method. Normally standard method will tell you in detail on how to treat the sample. The next step is replicate samples. Okay, in analytical chemistry, replication is important. Okay, so you must have minimum of 3 replicate samples. The more is better. Okay, so what does replicate sample means? Okay, it means a portion of material of approximately the same size that undergo the same analytical procedure, same time, same way, same manner. Okay, because replication normally would improve the quality of the results and also minimize error. So you want to analyze river water sample, so you must analyze it 3 times minimum. Okay, sample 1 you take 100 ml, for example. Sample 2 also 100 ml. Sample 3 also, replicate 3 also must be 100 ml. So the same mass, the same size, the same treatment. Okay, and then you get um, 3 uh, replicate values or data. From there you find the average. Okay, so the purpose of replicate is to minimize error. From the 3 samples you can see the result will be more or less the same. Okay, and then let's say when you do 3 analysis, suddenly the result is way too high or way too low compared to the other 2, so that will indicate something went wrong during the 3rd replication analysis. Probably during that time power outage happened. Okay, blackout. Okay, so it leads to error in the analysis. Okay, especially when it involves usage of instrumentation that use electricity. So that means you have to repeat the analysis. So that's why it's important to do replication. Okay, so that you minimize error. So the next step 6, is to prepare solution of sample. Okay, if your sample is liquid form, what are the solvent chosen? If your sample in solid form, also what are the solvent chosen? Okay, to dissolve the sample. Okay, without decomposing the analyte. Okay, normally solvent are um, sam- uh, acids such as nitric acid, sulfuric acid, hydrochloric acid, and many more. Okay, so these samples will um, dissolve solid sample. For example, if you obtain soil sample tanah, so awak nak cari heavy metal content of the soil, so you have to digest the sample. Digest mean you dissolute, okay, awak dissolve tanah tu dalam acid. So acid chosen are like nitric acid, sulfuric acid, and so on. Okay, the seventh step is eliminating interference. Okay, so this step is to prevent error that due to the presence of interference. For example, awak collect a river water sample just now. Okay, you have to eliminate interference such as the dry leaves, okay, uh, dried sticks, okay, solid samples. You have to eliminate them first by filtration. Okay, so that's what it means by eliminating interference. So you don't want that solid sample in the river water to interfere with the analysis. Okay, the eighth step, the second last step, is to measure the property of the analyte and calibration. Okay, so what are the analysis to be done on the sample? So it goes back to the method just now. So if your method is to determine the pollution, to identify whether river water is polluted or not, what are the method? Okay, method will need to determine chemical oxygen demand, for example, biological oxygen demand, BOD. So what are the and standard method to measure BOD, COD? Okay, and to measure BOD, COD, you have to calibrate first the instrument, the meter to measure BOD and COD. Okay, so that's what it means by calibration. Okay, so calibration means you calibrate first the instrument uh, with standard solution before you measure your sample. Okay, for example, when we measure when we have soil sample just now, soil sample to measure the heavy metal content, so it's subjected to AAS, absorption, atomic absorption spectrometer. Okay, so you have to calibrate the AAS machine first. Okay, calibrate. Okay, let's say the first metal to be determined is iron, for example. So use the standard iron solution, okay, to prepare a different concentration. Let's say the standard is prepared at 100 ppm. Okay, that is the standard. Okay, and then it's further diluted into 5, okay, different concentration. When we calibrate, we must have at least 5 standard. Okay, 5 standard. So let's say we have 20 ppm, 40, 60, 80, and 100 ppm. So these are the concentration of the standard iron solution. Okay, so what are the solution used to prepare this? Let's say you use distilled water. So distilled water will be the blank. Okay, distilled water. Okay, so let's say you use distilled water to prepare this standard solution. So the distilled water only will become the blank. So of course the blank will have 0 ppm. So this is the ppm. This is the absorbance of the AAS instrument. Okay, AAS. So you must have a straight line. Okay, standard calibration curve. Okay, so this is 20, 40, 60, 80, 100 ppm. So probably you get somewhere here, somewhere here, somewhere here, here. Okay, it's line of best fit. Okay, then you run your sample. Okay, using the same instrument. So the sample will gives you the instrument will give you the absorbance of the sample. So based on the sample obtained, like say the value is here, okay, then you use the calibration curve to find the concentration, okay, the concentration of iron in the sample. So this is the importance of having calibration. Okay, so this is example of calibration. Okay, okay, so this is the explanation of calibration. So there are few types of standard solution. They are categorized as primary standard, secondary standard, NIST standard, or SRM standard. Okay, finally the last step is data analysis. This is where you analyze the data obtained. Okay, and then once you analyze the data, you conclude the first step, which is defining problem. Means you are answering the problem. Okay.